I want to do an example problem of an object in free fall. But in this case, I want to do a little more complicated than the simple ones I did before. So let's consider the following. You see a water balloon thrown up go past your 1.4 meter dorm window in 0.15 seconds. When will it reappear? How high above your window did it go? This is the type of problem that many students that I've had will read, they'll stare at it for a while, and then come to me and say, I have no idea where to start. And so one of the key parts in developing a good problem-solving strategy is, what do you do when you read a problem and after reading it, you don't know how to solve it? Well, the answer always starts with a large stack of blank scratch paper. So that's the first thing you got to get is a lot of scratch paper to make sketches and schematics and for brainstorming purposes. But once you have some scratch paper, it always starts with visualize. Okay, reading it again, what is going on, and drawing a picture to see what is happening. Okay, I have a water balloon that's thrown up. It goes past my 1.4 meter dorm window. Okay, so I have a dorm window. The problem says my dorm window is 1.4 meters, so that's got to be the height. That's the only real height that makes sense, because they're saying this water balloon is thrown up, and so it goes past here the 1.4 meter dorm window, and this time interval then, this 0.15 seconds, has to be 0.15 seconds, the time interval that it takes to go across the window. Okay, fine. So this is what's happening. When will it reappear? How high above your window did it go? Okay, so what happens? So it goes, the water balloon goes past the window and then goes out of sight, and it goes up. It goes up to some height, and then it's going to come back around. Now, I want it to be one-dimensional. It's going to come back on itself, but that's a little hard for me to visualize. So I'm going to just draw it slightly to the right, so I know that, okay, it's coming back down. And so eventually it's going to reappear and go past the dorm window again. Okay, so it goes up, it passes the window the window's this has a height of that much visual space. It traverses in that time. It's going to go up and come back down. Okay, so I think now I've spent some time and I have a good idea to visualize what's going on. Now what? Okay, well, what sort of physics applies to the problem? Okay, so I mean, this is obviously a free fall problem. It's one dimension. It's going to come back and fall back down on its same trajectory, so I can treat it all as one dimensional. We're going to neglect air resistance and all of that. We'll do particle model, and since it's in free fall, we can go back to our constant acceleration equations. Okay, so I think that's pretty clear. Not too much work to come up with the physics that's going to apply. And we had these handy expressions that related initial and final positions and velocities in two specific points in time. And since that's part of my toolbox, and I think that's the physics that's going to apply to those equations, to this problem, I might get those tools out right away. So I have some, and if it's 1D, I'm going to call my axis x eventually. My final x component of the velocity is my initial component of the velocity plus the acceleration times delta t. My final position is equal to my initial position plus my initial velocity times time plus 1/2 times the acceleration times the time interval squared. And also I had this third equation, which was sometimes useful, that said my final velocity squared is equal to my initial velocity squared plus twice the acceleration times the displacement. Now again, I remember that these aren't fundamental physics equations. I derived them under very specific conditions, but since I have those specific conditions in this problem, I think that's going to be a handy tool to have. In fact, to be honest, when I'm solving a lot of these, I might put these sorts of equations on a little index card and keep it by my large stack of blank scratch paper so I always have them available and they're with me to use. Okay, so now, what points in time should I look at? I mean, these relations apply to two specific points in time, an initial time and a final time. So for this problem, which two should it be? You know, there's lots of points in time. It crosses the threshold here, the time it disappears, the time it gets to the top, the time that it reappears. And so here's a point where a lot of students will then stop and then come to me and ask, I don't know where to go on. I don't know what times to choose. And if you don't know what times to choose, your best bet is to simply choose any two that seem reasonable, and see what you find. This is still part of the brainstorming session. We're still brainstorming. And sometimes you'll do preliminary or internal calculations during your brainstorming session to see what else you know and what else you can figure out, what other information you can come up with. Okay, so what are some logical places to do? Well, to be honest, what a lot of students will say is they'll go to sort of part A in this question, which is here. When will it reappear? And they'll say, okay, I'm going to choose as my points in time, one of these two when it enters the window, when it leaves the window, and make the final time when it reappears and see what ends up happening. And that's a perfectly valid thing to do. But I'm going to tell you something as a sophisticated problem solver. That's not, in fact, the first place I would start. I don't know exactly how this is all going to come together. But I'm still in my brainstorming point of view. I'm not set to just go ahead and try to solve the problem. The 2 points in time that I'm going to look at first are these two. The point of time where it enters the window and the point in time where it leaves the window in the initial path up. Even though those 2 times, the initial and final time, are not the times that I'm looking for. How high above the window did it go? Well, that's this time here, at the height of the trajectory. When did it reappear is when it comes back. I'm not, in fact, going to start there. And the reason is the information I'm given gives me information about these 2 times, these initial and final times of the balloon crossing the window. And as a sophisticated problem solver, I'm going to take that as a hint, and I'm going to start where I know things and use that information to build and to gather more information from there. All right, so I'm going to choose these 2 times to start, initial and final, and I'm going to decide sort of what I know and what I can figure out. I'm still really still in brainstorming mode. So at these points in time, I have some initial time, which I'm going to call 0. I have some final time, which, since it took 0.15 seconds to go the entire way, is 0.15. And now I need to find positions. All right, to do that, I need a coordinate system. Let's go back. So where should my coordinate system be? I need a 0 and a positive direction. I'm going to choose my 0 to be at the bottom of the window, and I'm going to choose the positive x direction to be up. In these problems, every schematic needs a coordinate system with an origin and a positive direction. If you don't have that, then that should be a clue that something's amiss. Okay, so given that coordinate system, I have some initial position, which is when it crosses the 0. Well, that's 0 given that coordinate system. Some final position, which given the 2 points in time that I've chosen, that's a positive 1.4 meters. And then I have a initial velocity in the x, which is, I don't know what that is. and then well, it's not 0. I don't know what it is. It's unknown. And then a final velocity in the x, and I don't know what that is either. I do know my acceleration because I'm in free fall, and so that has a magnitude of g. And given this coordinate system, where positive is up and negative is toward the center of the Earth, then the direction of my acceleration is negative. Okay. So what does this information tell me? Well, look, I don't know what these are. So the next step, if I'm going to gather more information, would be to use what I have here to come up with this. And then I would know more about the trajectory than I do now. And I have a lot of information here. That's why I started with these two initial and final times. And so what can I do to solve that? Well, right here, this equation has final and initial position, acceleration, time interval. I know all that information. The only parameter in here is the initial velocity that I don't know, so I can use this equation to solve for the initial velocity. Okay, so let's do that. The final position, I'm just going to plug in numbers now, because I have one equation, one unknown. My my final position, 1.4, is my initial position 0 plus initial velocity unknown times the time, which is the final time, right? So this is the time interval. So this is the final time, 0.15, and then plus 1/2 the acceleration, which is negative g, times the time squared, 0.15 squared. A little round of space there, but it's 0.15 squared. We will use g for these systems to be 9.8 meters per second squared, sort of standard acceleration for velocity. And I can go ahead and solve that then for v initial. And I'm not going to do all the algebra, but if I solve that, I find that the initial is 10.068 meters per second. And you can check that if you want to plug in the numbers. Okay, so my initial velocity, or the velocity when it passes the first threshold, is 10 point. And I'm going to keep 5 significant figures since this is it doesn't have 5, but it's an internal calculation, so I want to keep a lot of numbers so I don't lose significance due to rounding errors for an internal calculation. And using that now, I can find the final velocity because I have that expression, and so that's the initial velocity, which I know, plus the acceleration, which is negative 9.8 times t final, which I know, 0.15 seconds. And if I solve that, and you can check my arithmetic, that's equal to 8.598 meters per second. And that makes sense because it's slowing down as it goes up. And so I can include that information here. This is 10.068 and 8.598. So what is this? And so I've identified these as this initial velocity and final velocity, but it means more than that. That's just sort of code for this particular internal calculation. What this initial velocity here is the velocity of the particle when it crosses the first threshold. And this 8.5 is the velocity of the particle, or the balloon in this case, my particle model, when it exits the window. So I have the velocity exactly when it leaves the site of the window. Well, that's incredibly useful information. With that velocity, I think I can now figure out how high it goes. And that, in fact, is the second thing I'm looking for. So I can do that right away. And so let's now look at 2 different points in time. Now I want to look at t initial point of time is when it leaves the top part of the window, and the final point of time is when it reaches its top height. And now the question is, what about my coordinate system? Do I have to use the same coordinate system that I did before? And I don't. I can have a new coordinate system. I'm going to have a new 0, which is at the placement of the initial time, where I'm going to have positive x going upward. And we'll finish this example in the next module.